Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this video we are going to determine the bandwidth of the interference pattern produced in a wedge-shaped film. So how is it that we're going to determine the bandwidth? For this, we are going to assume that we know the expressions for the constructive and destructive interference. So we are going to assume that we know these particular expressions and we are going to start from there. Let us quickly recollect what we have done in the interference pattern of a thin wedge-shaped film. Here is the diagram. So we have alpha, which is the wedge angle. We have an angle of incidence of the monochromatic light, which is I, and this is the reflected ray R1. This particular ray is transmitted. It once again is reflected from the lower plate of the wedge shape, and this actually will get reflected, and R2 is once again the transmitted one. So we are getting an interference pattern due to the interference between these two ways, R1 and R2, and the path difference between the two is coming out to be delta is equal to 2 mu t into cos of alpha plus R. Let us now modify this expression, or rather simplify this expression for normal incidence. Now whenever there is normal incidence, so instead of having the ray coming on this way, the ray is actually coming on this way. Now when it comes in this way, this direction, the angle of incidence is going to be 0, and so also your angle of refraction, which is going to be equal to R. Since that is going to be equal to 0, this expression for the path difference between the rays R1 and R2 is going to be equal to 2 mu t into cos of alpha is equal to delta. And then we equate this particular expression for the conditions for constructive and destructive interference. Let us see how we do that. So the expression for the path difference is going to be equal to delta is equal to 2 mu t into cos of alpha plus R. Your R is going to be equal to 0 since your I is going to be equal to 0, and hence your delta is going to simplify to delta is equal to 2 mu t into cos of alpha, which is nothing but the wedge angle. And this is now equal to 2n plus or minus 1 into lambda by 2. This will be for the constructive interference, which actually simplifies to 2 mu t into cos of alpha is equal to 2n plus 1 into lambda by 2 for n is equal to 0, 1, 2, 3. And this is going to be equal to 2n minus of 1 into lambda by 2 for n is equal to 1, 2, 3. And both these cases are for the maximas or for the constructive interference. Similarly, I equate this expression 2 mu t into cos of alpha. I equate it to n lambda because this is the situation where you are going to get the condition for the destructive interference, wherein n is equal to 0, 1, 2, 3, or rather the minimas, the condition for the minima. Alternatively, the thickness at the different minimum points is going to be equal to n lambda upon 2 mu into cos of alpha. Normally the wedge angle is very small, and therefore this I can write it as T is approximately equal to n lambda upon 2 mu into alpha. So this is the expression that we are getting for the thickness, wherein n is the integer, lambda is the monochromatic wavelength with which we are illuminating the wedge-shaped film, and this is going to be equal divided by 2 into wherein t is equal to n into lambda, wherein n is the integer from 0, 1, 2, 3. Lambda is the monochromatic wavelength with which we are illuminating the wedge shaped film, divided by 2 into mu, which is the mu is nothing but the refractive index of the wedge medium refractive index, and alpha is nothing but the wedge angle. So we need this expression. Let us call this expression as, let us say, A. And I'm going to use this frequently in order to find out the bandwidth of the interference pattern produced by a wedge-shaped film. Here is the wedge-shaped film with an angle alpha and with normal incidence. So the rays of light are actually falling normal.
Repeat.
So here is the wedge-shaped film with an angle of wedge equal to alpha. We are actually having normal incidence over here, and at this particular point D and F, for this thickness, we are going to have the dark bands. And we know that suppose it is going to be dark bands, then the condition for the thickness at this point and at this point will be T is equal to, this is going to be equal to N into lambda divided by 2 mu into alpha, wherein we are assuming that alpha is very small. So the first thickness T1 will actually be equal to 0. This is going to be equal to 0, 1, 2 and 3. So for the first band, the thickness is going to be 0 for the first band. Then, or rather, the first band will appear at the thickness 0. The second one is going to appear, I substitute 1 in this expression, and this will turn out to be lambda upon 2 mu into alpha. And after that, you are going to have your, for the third one, lambda upon 2 mu into alpha, and this is multiplied by 2 because this is going to be equal to 2 over here, and therefore because this is going to be equal to 2 over here, and therefore this is going to be equal to T3 is equal to lambda upon 2 mu into alpha. So from here actually we are trying to find out what is the expression for the bandwidth. So now from here one can very well see that tan of the angle alpha is going to be equal to opposite side EG divided by the adjacent side, which is going to be equal to CG, which can be later simplified to EG is nothing but this is going to be equal to EF minus of GF, this divided by CG, which can once again be simplified to EF minus of GF is equal to CD minus of CD, and this can then be divided by your CG is actually equal to your DF. So your alpha, because if at all your alpha is very small, then your alpha will be equal to EF minus of CD upon DF. So this is going to be, so what is your EF? EF is nothing but the thickness at this particular point, and that thickness is actually equal to, and this thickness is actually equal to, alpha will actually be equal to EF minus of CD divided by DF. We know it very well that in all these cases that we have done, we have this value alpha. But since it is cos of alpha, and since your alpha in itself is very small, therefore it is almost equal to 1, because cos of 0 is actually equal to 1. Hence, for all these cases over here, what will transform is your T2 is going to be equal to lambda upon T mu, and over here this is going to transform to T3 is equal to lambda upon only mu, because this and this is going to get cancelled, and therefore you are going to have two expressions out over here, your T3 and that for your T2. Alpha is now equal to EF minus CD upon TF, but what is EF? EF is nothing but your T3, and what is CD? It is the thickness of the second dark band, which is going to be equal to T2, and this divided by your DF. DF is nothing but the bandwidth, because you have one dark band over here, you are having another dark band over here. The distance between two consecutive dark bands is going to be your bandwidth, which is going to be equal to beta. Substituting the values, your alpha is going to be equal to lambda upon mu minus of lambda upon 2 mu, and this entire thing will be divided by your beta, and thence your alpha will actually be equal to lambda divided by 2 mu into beta. So this is the final expression for the wedge angle. But from this you can also find out your beta, which is going to be equal to lambda upon 2 mu into alpha, and this is how actually you can find out the bandwidth. Now in this case, you need to, normally by optical measurements you can find out the bandwidth, and since you know the bandwidth, since you also know the wavelength, you can find out what is the wedge angle, which is alpha. So here actually we are completing how to find out the bandwidth. Let us take quickly one of the applications of this particular method. Let us go back to our original figure. Here is the original figure. So we have, let us assume that at this we are placing maybe a piece of paper, or we are actually placing maybe a small wire with a cross section, something like this. So this is a very good method to find out either the diameter of the wire, or to also find out what is the thickness of the thickness of a paper of a rectangular, with a rectangular cross section. Let us apply this method of the bandwidth for finding out either. Let us apply this method for finding out either the width of the paper or for finding out the cross-sectional diameter of a very thin wire. So in the case of, let us assume that we are having a cross-section, a very thin wire, and we want to find out what is the diameter of this. Now since we want to find out what is the diameter, this is your alpha, which is the wedge angle that is being made by this wire. This is the distance L at which the wire is actually placed, and therefore your tan of alpha is going to be equal to opposite side D upon the adjacent side, that is length. L is nothing but the distance at which the wire is kept from the edge or from the point of contact of the two glass plates of the wedge-shaped film. So tan alpha is equal to this, is equal to D upon L. Therefore, approximately alpha is going to be equal to D upon L. I'll put it approximately over here. So can we equate this expression and this expression? Yes, we can do that. So we can equate this expression to this expression because both of them are expressions for the wedge-shaped film. And therefore, this is going to be equal to D upon L is equal to lambda upon 2 mu into beta. And hence, your diameter D is going to be equal to lambda into L divided by 2 mu into beta. So it is this particular expression that will actually allow you to find out what is the diameter of the thin wire that actually makes a wedge of angle alpha and placed at a distance L from the point of contact of the two plates in the wedge shape film. So we have studied an expression for the bandwidth for the interference pattern produced by a thin wedge shape film, and we have also studied an application based on that. Sincere thanks, students, for watching this particular video. Stay tuned to Ekeeda and do subscribe to Ekeeda. Thanks a lot.